In the skipgram model, we use the Softmax operation to compute the conditional probability for generating the context word WO based on the given central target word WC. This is what we got, and then later after that we arrived at the log loss. Looking at the loss function, you can see there is a sum for the whole dictionary. This sum also appears in the derivative of the loss function. This happens to both the skipgram and the Seabound models. So the overhead for computing the gradient is too high. That is why the approximate training method came in the picture, including the negative sampling and the hierarchical softmax methods. Given the context window for the central target word WC, the probability of the event for the context word WO to appear in the context window is this. The probability for a variable D is equal to 1 given the word WC, the central target word, and the context word WO. D equal to 1 means the context word WO appears in the context window. So this is a function of the two words or the two word representation U0 and VC. We use the sigmoid activation to model the probability. We consider maximizing the joint probability of all the events in the text sequence. So what does it mean? With the outer product, we consider each and every word in the text sequence as the central target word WT, right, with T from 1 to the max length of the sequence. And for each central target word WT, we consider M words before and M words after it. That's why we see J is from negative M to M for all the context words. Also notice that we only consider D equals to 1, meaning the context words appear in the context window. This is just like writing the probability of a target Y is equal to 1 and the probability of the target Y is equal to 0. Examples with the true values of the target is equal to 1, we call them the positive example. Otherwise, we have negative examples. So what negative sampling does is to add negative examples in here so that it makes the objective function more meaningful. Let's assume that the event P occurs in or when the context word WO to appear in the context window of the central target word WC. So this is a positive example. We then sample keywords not appearing in the context window as the noise words, and these are the negative examples. We assume the event for the noise word WK, for K from 1 to K, to not appear in the context window of the central target word WC is NK. So the event P is for the positive example, and the event NK for K from 1 to uppercase K are the events for the negative examples. And we assume that these are independent. Now we rewrite the joint probability considering the negative examples as well. In here we no longer see D equal to 1, which is just for positive examples. The probability of the context word given the central target word here could be approximated by the product of the context word to appear in the context window of the target word, and this probability is just for the positive example. The product after it is for the negative examples, in which we consider the probability of the context word WK not to appear in the context window of the target central word WT. Now taking the log of the both sides, we get this. The product becomes the sum. Now replace the probability using the sigmoid function, and here we use the sigmoid function to model the probability and replace the context word by its word representation, the central target word by its word representation as well. We do the same thing here, and eventually we get to this. Looking at the sum, we could see that this sum doesn't depend on the whole dictionary. Taking the gradient or the derivative of the log loss, we still have the sum in there, and the sum doesn't depend on the whole dictionary size, and it is just related to k. When k is small, then we have lower computational overhead for each step. Hierarchical Softmax is another type of approximate training using a binary tree. In the binary tree, the leaf nodes represents every word in the dictionary. W1, W2, etc. up to the last word in the dictionary. For the word W, LW is the number of nodes on the path from the root to the leaf node of the word W. For example, LW3 would be equal to 4 because there are 4 nodes. The root is the second, the third, and the fourth. Also, we denote NWJ as the J node on the path with the context word UNWJ. For example, the root is the first node, this is the second node, and that is the third node on the path. Now let's approximate the conditional probability in the skip-gram model. The probability of the context word WO given the central target word WC is the product of a number of terms. For each term, it is basically a sigmoid function of the inner product of the word representation of the context word and the central target word. Traversing the tree from the root down, if we traverse to the left, then this term is positive, otherwise it is negative. For the context word WO, we traverse from the root until the node just before it. Let's take an example. From the tree, we calculate the probability of the word, the context word W3 given the target word WC. So apply the approximation, and what we get is this. This is when we traverse to the left, and this is when we traverse to the right, and that's why we see the negative sign. And this is when we traverse to the left again. Notice that the sigmoid function of x plus the sigmoid function of negative x is equal to 1. Applying this, we can prove the sum of the probability of the context word W given the central target word WC for all the whole dictionary is equal to 1. We can see that easily in a special case. If we have just 2 words in the list, then we have this for probability of W3 given WC, and we can easily write P of W4 given WC, which is very much similar, except this side is positive. So then apply this, and apply this. The sum of the sigmoid function for x and the sigmoid function for negative x is equal to 1. Applying this, then easily you get the sum of this probability and the sum of that probability in the case that there are just 2 words, and that is equal to 1. And that is to verify this for a special case. The time complexity for traversing the path from the root to the node just before the leaf of the context word is in the order of log with base 2 of v. So here we can see that the computational overhead for each step in the hierarchical softmax training is much reduced.